Light enters physics as a measurable carrier of energy, momentum, and information, described with numerical precision and tested across more than a century of experiment. In modern theory, light is understood simultaneously as a classical electromagnetic wave and as a quantized excitation of a field, with both descriptions converging on the same invariant propagation speed in vacuum. C equals 299.792.458 meters per second, exactly by definition of the SI system. This number does not emerge from astronomy or optics alone. It arises from the structure of the electromagnetic field itself. In classical electrodynamics, light appears as a self-propagating oscillation of electric and magnetic fields. These fields obey a coupled set of differential equations formulated in the 19th century by James Clerk Maxwell. When the equations are combined in empty space, they predict wave solutions whose speed depends only on two constants, the electric permittivity of free space and the magnetic permeability of free space. Their product fixes a single velocity. When this velocity was evaluated numerically, it matched the best optical measurements of light speed available at the time. Light revealed itself as an electromagnetic phenomenon before anyone asked how fast it travelled. This speed emerges mathematically from the wave equation itself. The second-order time derivative of the electric field balances a second-order spatial derivative multiplied by the inverse square of c. The field evolves in such a way that disturbances propagate at that fixed rate, independent of frequency, polarization, or source motion. Once emitted, the wavefront advances through space with a geometry defined entirely by this constant. At this level, light functions as a signal, a change in the electromagnetic field that carries energy density, momentum density, and phase information from one spacetime point to another. The Poynting vector quantifies the directional energy flow. The stress-energy tensor encodes how the field transports momentum and exerts pressure. Each of these quantities propagates at the same invariant speed. Information encoded in amplitude modulation, phase shifts, or polarization structure rides on this propagation without outrunning it. Quantum theory refines this picture without altering the speed limit. In quantum electrodynamics, the electromagnetic field becomes an operator-valued field, and light consists of discrete quanta called photons. Each photon carries an energy proportional to its frequency, given by Planck's constant times the oscillation rate, and a momentum proportional to its wave vector. Despite this particle-like description, photons propagate along null trajectories defined by the same constant c. The quantum formalism preserves the classical light cone structure exactly. A photon exhibits zero invariant mass. This property places it on a special class of trajectories in spacetime, where the spacetime interval between emission and absorption equals zero. Along such paths, proper time does not accumulate. The equations governing photon propagation therefore involve spacetime geometry directly rather than an internal clock. This geometric role explains why the speed of light remains invariant across all inertial reference frames. The phrase "speed of light" often suggests a property unique to visible radiation. In practice, the constant c governs all massless field excitations. Radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays all propagate at exactly the same speed in vacuum. Differences among them appear in frequency, wavelength, and interaction strength with matter, while propagation speed remains fixed. The electromagnetic spectrum spans more than 20 orders of magnitude in frequency, from kilohertz radio waves to gamma rays exceeding 10 to the power of 20 Hz, yet the wavefront velocity remains unchanged. This invariance leads directly to a deeper interpretation. The constant c functions as the maximum speed at which causal influence can propagate. Any physical interaction that transfers information from one event to another does so within the light cone defined by this speed. Electromagnetic signals, gravitational waves, and quantum field disturbances all respect this limit. The geometry of space-time itself organizes around it. Information here refers to physically distinguishable states. A change in field configuration, particle number, or energy distribution constitutes information when it can influence a future measurement. The propagation of such influence demands a finite time separation. The speed of light therefore becomes the speed of information in the most general physical sense. No signal, regardless of encoding or medium, carries causal influence faster than c in vacuum. Mathematically, this restriction appears as hyperbolic partial differential equations governing field evolution. Hyperbolic equations possess characteristic surfaces that limit the domain of dependence of solutions. For electromagnetism, these characteristic surfaces coincide with light cones. A disturbance at one space-time point affects only points lying within its future light cone. Points outside remain causally disconnected at that time. This structure enforces determinism and preserves temporal order. Energy transport obeys the same bound. The energy flux of an electromagnetic wave equals the product of energy density and propagation speed. Since the energy density remains finite, superluminal transport would require violations of field equations or negative energy densities. Neither arises in experimentally verified regimes of physics. Momentum transport follows a related rule. Radiation pressure results from momentum carried by photons striking a surface. The rate of momentum transfer depends on the arrival of photons, which occurs at speed c. Even in high-intensity laser systems, where trillions of photons interact per second, the front edge of the pulse advances at the same invariant speed. The universality of this limit appears across independent experimental domains. Precision time-of-flight measurements using synchronized atomic clocks confirm electromagnetic signal speeds with uncertainties below 1 part in 10 billion. Interplanetary ranging experiments verify that radar echoes from distant spacecraft return exactly when predicted by light speed propagation corrected for gravitational curvature. Modern interferometry defines the meter itself by fixing c and measuring elapsed time. Within quantum theory, the concept of information propagation acquires additional nuance. Quantum states exhibit correlations across space through entanglement. These correlations display statistical structure across arbitrary distances, yet measurement outcomes remain locally random. No controllable signal travels through entanglement faster than c. The mathematical framework enforces this through commutation relations that vanish outside the light cone. Observable operators at space-like separation commute, ensuring causal independence. This feature maintains consistency between quantum mechanics and relativistic causality. Even when wave functions extend over large spatial regions, physically extractable information remains bounded by light speed propagation. The formalism preserves causal order without requiring a preferred reference frame. From an operational standpoint, every measurement of distance reduces to a time measurement multiplied by c. Radar ranging sends a light pulse to a target and records its return time. Astronomical distances derive from light travel times combined with geometric inference. Even spatial coordinates in relativistic physics emerge from clock synchronization procedures constrained by signal speed. Space and time intertwine through c at the most fundamental level. This role elevates the speed of light from a property of a specific phenomenon to a structural constant. It links temporal intervals to spatial separations. It converts seconds into meters. It defines causal reach. It governs the transformation laws between reference frames. In modern unit systems, its numerical value remains fixed by convention, while experimental effort refines time measurement itself. Light therefore functions as a physical signal in the deepest sense. A field excitation whose propagation establishes the limits of cause, energy transfer, and observable influence. Its speed does not depend on source motion, observer motion, frequency, or amplitude. It arises from the equations governing fields and space-time together. In this framework, asking how fast light travels becomes inseparable from asking how reality transmits change. The constant C encodes that answer with mathematical precision, anchoring electromagnetism, quantum theory, and space-time geometry into a single causal structure. Light entered measurement long before it entered theory. Long before equations described fields or quanta, observers treated light as a phenomenon whose speed could, in principle, be determined using geometry, timing, and astronomy. The path toward recognizing a finite speed unfolded gradually, driven by increasingly precise observations rather than sudden conceptual revolutions. Each step refined the idea that light propagation involves duration, distance, and measurable delay. In the ancient world, light was often treated as instantaneous because everyday experience offered little incentive to think otherwise. Terrestrial distances appeared small compared to the rapidity of visual perception. The human nervous system responds on timescales of tens of milliseconds, while light crosses a room in a few nanoseconds. This disparity placed direct perception far outside the regime where delay could be sensed. As a result, early philosophers focused on the nature of vision rather than its timing. Greek thinkers debated whether vision involved rays emitted from the eye or impressions carried inward from objects. Both frameworks allowed light to act with extreme rapidity. The absence of observable delay reinforced the intuition that speed measurements would yield values far beyond practical resolution. Geometry dominated optics, while time remained secondary. During the medieval period, optical theory advanced through lenses, mirrors, and refraction laws, yet the speed of light remained unquantified. Scholars refined ray tracing and image formation while treating propagation as effectively instantaneous. Experimental limitations preserve this view. Mechanical clocks lacked the precision needed to resolve extremely short intervals, and distances large enough to amplify delay lay beyond controlled experimentation. The transition from philosophical speculation to measurement required astronomy. Celestial distances extended propagation times into ranges detectable by human-made clocks, provided periodic phenomena offered reliable timing markers. The solar system became the laboratory in which light's speed first revealed itself. The decisive step occurred in the 17th century through the work of Ole Rømer, an astronomer studying the motions of Jupiter's moons. Jupiter hosts several large satellites whose orbital periods can be predicted with high regularity. Among them, Io completes an orbit in approximately 42.5 hours, producing frequent eclipses as it passes into Jupiter's shadow. These eclipses serve as natural clocks, visible from Earth with telescopic observation. Rømer noticed a systematic pattern in the timing of Io's eclipses. When Earth moved closer to Jupiter in its orbit, the eclipses appeared to occur earlier than predicted. When Earth moved farther away, the eclipses appeared later. The discrepancy accumulated gradually over months, reaching several minutes. This pattern correlated directly with Earth's changing distance from Jupiter as both planets orbited the Sun. The key insight involved geometry and orbital motion. Earth's orbit introduces a baseline variation in distance of roughly the diameter of its orbit, about 300 million kilometers, or roughly 186 million miles. If light required time to traverse this additional distance, eclipse signals would arrive later when Earth lay farther from Jupiter. Rømer interpreted the accumulated delay as evidence that light propagation involved finite time rather than instantaneous transmission. By analysing the total delay accumulated over half of Earth's orbit, Rømer estimated the time required for light to cross the diameter of Earth's orbit. His value corresponded to a speed on the order of hundreds of thousands of kilometers per second, within the same order of magnitude as the modern value. While his numerical estimate lacked modern precision, the conceptual breakthrough proved decisive. Light speed could be measured. This astronomical measurement carried significant implications. It linked time measurement to spatial distance through celestial mechanics. Orbital dynamics supplied predictable timing, while geometry supplied distance. Light served as the intermediary, whose propagation converted spatial separation into temporal delay. The response to Romer's conclusion unfolded gradually. Some contemporaries expressed skepticism, questioning whether orbital irregularities or observational errors could explain the timing shifts. Over time, independent confirmations strengthened the case. Subsequent astronomers refined the analysis using improved telescopes and better orbital models, reinforcing the interpretation of finite propagation speed. The realization reshaped optics and astronomy. It demonstrated that light behaved like a physical entity traveling through space rather than an instantaneous influence. This view aligned naturally with emerging mechanical philosophies of nature, which favored finite transmission of effects. Following the astronomical breakthrough, physicists sought terrestrial methods to measure light speed directly. Earth-based experiments offered greater control over distance and instrumentation, though they demanded exceptional precision. Measuring a signal that traverses kilometers in microseconds posed formidable challenges to 17th and 18th century technology. One early terrestrial approach involved rotating mirrors. A light beam reflects off a rapidly spinning mirror, travels a known distance, reflects back, and encounters the mirror again after a brief interval. During that interval, the mirror rotates slightly, altering the return angle. Measuring this angular displacement allows calculation of the light's travel time and speed. This method matured in the 19th century through the work of Hippolyte Fizeau and Léon Foucault. Fizeau employed a toothed wheel rotating at high speed, sending light through gaps between teeth toward a distant reflector. At certain rotation rates, returning light aligned with a tooth rather than a gap, producing extinction. The rotation rate at which this occurred encoded the light's round-trip travel time. Fizeau's 1849 experiment used a baseline of about 8.6 kilometers, or roughly 5.3 miles, between Montmartre and Suresnes, near Paris. His measured speed approximated 313,000 kilometers per second, within a few percent of the modern value. This result marked the first successful terrestrial determination of light speed. Foucault refined the rotating mirror technique, increasing precision and reducing systematic error. His measurements improved accuracy and demonstrated that light travels more slowly in water than in air, confirming wave-based predictions of refraction. This finding provided independent support for wave optics and reinforced the physical reality of light propagation. These terrestrial experiments transformed light speed from an astronomical inference into a laboratory-measured quantity. They also revealed subtle dependencies on medium properties, introducing the concept that propagation speed varies with refractive index while maintaining a universal value in vacuum. Throughout this period, improvements in timekeeping played a central role. Mechanical clocks evolved toward higher precision, while optical methods converted spatial displacement into measurable angles or positions. Experimental ingenuity bridged the gap between extremely short durations and observable quantities. The gradual refinement of light speed measurements culminated in increasingly precise values. By the late 19th century, measurements clustered around 300,000 kilometers per second, with uncertainties shrinking steadily. The speed of light emerged as a stable numerical constant across independent methods and environments. This convergence prepared the ground for deeper theoretical insight. The consistency of measured values suggested an underlying principle rather than a contingent property. Experiments revealed light speed as invariant across source motion, observer motion, and direction within experimental resolution. These empirical facts later guided the formulation of special relativity. Before Einstein, the speed of light already occupied a privileged status in physics. It linked astronomical distances to time delays, laboratory baselines to angular deflections, and optical phenomena to mechanical motion. Each measurement reinforced the idea that light propagation obeyed precise, reproducible laws. The pre-relativistic era thus transformed intuition into quantification. What began as an assumption of immediacy evolved into a measured constant through careful observation, geometry, and timing. Astronomical cycles and terrestrial apparatus together revealed that light carries information across space with finite, measurable speed. By the time relativity reinterpreted the meaning of this speed, its numerical value and empirical robustness were already firmly established. Measurement came first. Theory followed. Electromagnetism entered physics as a quantitative theory through a unification of previously separate experimental laws governing electricity and magnetism. By the middle of the 19th century, experimentalists had established precise relationships between electric charges, currents, magnetic fields, and forces. These relationships existed as empirical rules, expressed through equations linking measurable quantities such as charge density, current density, electric field strength, and magnetic induction. What remained unclear was whether these phenomena described static interactions only, or whether they implied a deeper dynamical structure capable of independent propagation through space. That structure emerged through the work of James Clerk Maxwell, who reformulated known electrical and magnetic laws into a coherent mathematical system. Maxwell expressed these laws using differential equations that described how electric and magnetic fields vary in space and time. The resulting framework treated fields as physical entities distributed throughout space, capable of storing energy and evolving dynamically. The equations contained four central relationships. One linked electric fields to electric charge density, another linked magnetic fields to electric currents and changing electric fields. A third expressed the absence of magnetic monopoles. A fourth described how changing magnetic fields induce electric fields. Taken together, these relations encoded both static configurations and time-dependent behavior. Their full implications appeared only when Maxwell considered regions of space devoid of charges and currents. In empty space, the equations simplify. Charge density equals 0. Current density equals 0. What remains are coupled differential equations relating time-varying electric and magnetic fields to one another. When Maxwell combined these relations mathematically, he derived a wave equation. The electric field obeys a second-order differential equation in time and space, as does the magnetic field. The structure of these equations implies that disturbances in the fields propagate through space as waves. The speed of these waves emerges directly from the coefficients appearing in the equations. Specifically, the propagation speed depends on two experimentally measured constants: the electric permittivity of free space and the magnetic permeability of free space. These constants were already known from electrostatic and magnetostatic experiments measured using force laws and current balances. Their values carried dimensions that, when combined appropriately, produced a quantity with units of velocity. When Maxwell evaluated this velocity numerically, the result matched existing measurements of light speed obtained from astronomical and terrestrial experiments. The agreement extended beyond rough magnitude. The numerical value aligned closely with the best available optical data. This convergence revealed that light itself was an electromagnetic wave. This result carried conceptual weight. Light no longer appeared as a separate phenomenon requiring independent explanation. It emerged naturally from the dynamics of electric and magnetic fields. Optics became a branch of electromagnetism, unified under a single mathematical framework. The appearance of a fixed propagation speed carried additional implications. The value derived from electromagnetic constants did not depend on the frequency of the wave, the amplitude of the fields, or the motion of the source. The equations predicted a single characteristic speed determined entirely by the structure of the field equations. Once the constants were fixed, the speed followed inevitably. This prediction represented a departure from mechanical wave theories familiar at the time. Sound waves propagate through air at speeds determined by material properties such as density and compressibility. Water waves depend on gravity, depth, and surface tension. In each case, wave speed reflects properties of a medium. Electromagnetic waves, by contrast, propagated in empty space with a speed set by universal constants rather than environmental conditions. The constants themselves arose from experimental practice. Electric permittivity quantified how electric fields respond to charges. Magnetic permeability quantified how magnetic fields respond to currents. Both constants could be measured using laboratory apparatus involving charged conductors, coils, and force balances. Their values remained consistent across experiments and locations, reinforcing their status as universal parameters. The emergence of a wave speed from these constants suggested that empty space possessed electromagnetic properties. Fields stored energy in space itself. Energy density appeared proportional to the square of field strengths. Momentum density accompanied energy flow. Space became an active participant in electromagnetic dynamics rather than a passive background. The predicted speed carried numerical precision. Expressed in modern units, the value equals 299,792,458 meters per second. At the time, measurements carried larger uncertainties, yet the agreement with optical data fell well within experimental limits. This alignment offered strong evidence that Maxwell's equations captured a real physical mechanism. The wave solutions possessed additional structure. Electric and magnetic fields oscillated perpendicular to one another and perpendicular to the direction of propagation. Their amplitudes related through the same constants that fixed the wave speed. Energy flowed in the direction of propagation at a rate given by the product of field strengths and the propagation speed. These features matched known properties of light, such as polarization and energy transport. The fixed propagation speed raised an immediate question within 19th century physics. Relative to what frame did this speed apply? Classical mechanics operated within Galilean relativity, where velocities add linearly. Under that framework, a wave emitted by a moving source would exhibit different speeds relative to different observers. Maxwell's equations, however, predicted a single speed independent of source motion. Physicists attempted to reconcile this prediction with classical intuition by introducing a medium. This hypothetical substance, called the luminiferous ether, filled all space and served as the carrier of electromagnetic waves. The speed predicted by Maxwell's equations would then represent the wave speed relative to the ether. Observers moving through the ether would measure different speeds depending on their motion. The ether concept aligned with earlier mechanical analogies. Known waves required media. Elastic solids supported transverse waves, fluids supported longitudinal waves, light exhibited transverse polarization, suggesting a medium capable of sustaining transverse oscillations. The ether inherited these expectations. Yet Maxwell's equations themselves made no reference to such a medium. The fields evolved according to differential equations defined directly in space and time. Their energy and momentum resided in the fields, not in mechanical motion of an underlying substance. The equations functioned without modification in regions devoid of matter. Experimental tests soon targeted the ether hypothesis. Physicists attempted to detect Earth's motion through the ether by measuring changes in light speed along different directions. Interferometric experiments compared travel times along perpendicular paths, seeking shifts produced by orbital motion. The results consistently revealed the same propagation speed in all directions within experimental precision. These outcomes intensified the conceptual tension. The equations predicted a fixed speed. Experiments confirmed invariance. Classical kinematics struggled to accommodate both facts simultaneously. The issue persisted until a reformulation of space and time resolved the conflict. Before that resolution, Maxwell's equations already established light speed as a constant of nature. The constant emerged from laboratory-measured electromagnetic properties rather than astronomical observation alone. Its appearance within field equations elevated it from an empirical parameter to a structural feature of physical law. The unification achieved by electromagnetism extended further. Radio waves generated by oscillating currents exhibited the same propagation speed as visible light. Infrared radiation, ultraviolet radiation, and later X-rays all followed the same rule. The electromagnetic spectrum formed a continuum governed by the same equations and the same constant. The absence of a required medium marked a conceptual shift. Fields carried energy and momentum through empty space directly. The vacuum possessed structure encoded in constants. The propagation of influence occurred through field dynamics rather than mechanical displacement of matter. This realization influenced later developments in physics. Field theories became central tools for describing interactions. Forces emerged from exchange of field excitations. Space itself acquired physical attributes measurable through constants and response properties. Maxwell's equations thus introduced the first fundamental speed into physics as a derived necessity rather than an imposed assumption. The value linked electric and magnetic phenomena quantitatively. It unified optics with electromagnetism. It challenged existing notions of motion and reference frames. It established a constant that would later anchor space-time geometry itself. The recognition that light required no medium represented a profound shift in understanding. Propagation occurred through field self-interaction. Changing electric fields generated magnetic fields. Changing magnetic fields generated electric fields. This mutual induction sustained wave motion indefinitely through empty space. The speed of this motion remained fixed because the equations demanded it. Any alteration to the speed would require altering the constants or the equations themselves. Experiments repeatedly confirmed their stability. The constant endured scrutiny across decades of measurement. By the end of the 19th century, physics possessed a precise numerical value for light speed, a theoretical framework predicting its invariance, and a growing body of experimental evidence supporting both. The constant stood ready to reshape the foundations of kinematics and time measurement. The expectation of a preferred rest frame arose naturally from the mechanical worldview that dominated physics through the 19th century. Every known wave phenomenon required a medium. Sound propagated through air as compressions and rarefactions of matter. Water waves travelled through a liquid surface shaped by gravity and inertia. Elastic waves moved through solids as lattice vibrations. In each case, the wave possessed a well-defined speed relative to the material substrate that carried it. Motion relative to that substrate altered measured velocities through simple vector addition. This framework shaped intuition so deeply that extending it to light appeared unavoidable. Once electromagnetism identified light as a wave, the question of its medium followed immediately. Waves demanded something that oscillated. Electric and magnetic fields exhibited transverse behavior, suggesting resistance to shear rather than compression. Physicists therefore inferred a medium with unusual properties, capable of supporting transverse oscillations, extraordinarily rigid to permit extremely high wave speeds, yet offering negligible resistance to the motion of planets passing through it. This hypothetical substance became known as the luminiferous ether. The ether served a precise conceptual role. It defined an absolute state of rest. Maxwell's equations predicted a single propagation speed for electromagnetic waves. Within Galilean relativity, such a speed required a preferred reference frame. The ether provided that frame. Light travelled at speed, c, relative to the ether, while observers moving through it would measure speeds altered by their own motion. This view preserved classical kinematics. Velocities added linearly. Time flowed uniformly. Space existed as an absolute stage. The ether filled that stage and anchored electromagnetic phenomena to it. The task for experiment became clear: detect Earth's motion through the ether. Earth's orbital velocity around the Sun equals about 30 kilometers per second, or roughly 18.6 miles per second. If light propagated through a stationary ether, then the speed of light measured along Earth's direction of motion would differ slightly from the speed measured perpendicular to it. The expected difference amounted to a small fraction of c, yet precision optics offered a way to amplify such differences through interference. The most influential test emerged through interferometry. An interferometer splits a beam of light into two perpendicular paths, reflects them back, and recombines them to produce interference fringes. If light travelled at different speeds along the two arms, the travel times would differ. This difference would shift the interference pattern when the apparatus rotated relative to the ether wind created by Earth's motion. The experiment achieved its most refined form through the work of Albert A. Michelson and Edward W. Morley. Their apparatus, constructed in the late 19th century, rested on a massive stone slab floating in a pool of mercury. This design allowed smooth rotation while minimizing mechanical distortion. The optical path length extended through multiple reflections, increasing sensitivity to time differences on the order of a fraction of a wavelength. The predicted fringe shift could be calculated directly. If Earth moved through the ether at velocity v, the round-trip travel time along the arm parallel to motion would differ from that along the perpendicular arm by a factor proportional to v squared divided by c squared. With Earth's orbital speed, the expected shift equaled roughly 0.4 fringes for the apparatus used. This magnitude lay within detectable limits. The experiment produced a result that surprised the physics community. As the apparatus rotated, the interference pattern remained essentially unchanged. The observed fringe shifts corresponded to velocities far smaller than expected, consistent with zero within experimental uncertainty. Light appeared to travel at the same speed in all horizontal directions, regardless of Earth's motion. Michelson and Morley refined their measurements, improved alignment, reduced thermal gradients, and repeated the experiment at different times of year to capture variations in Earth's velocity. The null result persisted. Subsequent repetitions using different designs, materials, and locations reinforced the conclusion. The ether wind failed to appear. Physicists responded by modifying the ether hypothesis rather than abandoning it immediately. One proposal involved partial ether drag. According to this idea, matter moving through the ether dragged it along, reducing relative motion locally. Experiments measuring stellar aberration and optical effects contradicted complete drag, while partial drag introduced inconsistencies with electromagnetic theory. Another response introduced length contraction. Objects moving through the ether might physically contract along the direction of motion by just the right amount to cancel expected fringe shifts. This proposal preserved the ether while accounting for experimental results. Contraction appeared as an ad hoc adjustment, motivated by the need to save the medium rather than by independent physical reasoning. Time adjustments followed. If clocks moving through the ether ran at different rates depending on orientation or velocity, then timing discrepancies might vanish in specific experimental setups. These ideas introduced complexity without direct empirical support. The accumulation of null results extended beyond Michelson-Morley. Experiments using different wavelengths, vertical orientations, and varying altitudes all failed to detect anisotropy in light speed. Measurements of one-way light propagation proved challenging due to clock synchronization issues, yet round-trip measurements consistently indicated invariance. The failure carried deeper implications. Maxwell's equations possessed a symmetry incompatible with Galilean relativity. They predicted identical light speed in all inertial frames. The ether hypothesis attempted to reconcile this by assigning physical meaning to a specific frame, yet experiments refused to reveal it. As precision improved, the ether's explanatory power weakened. it contributed no new testable predictions beyond those already provided by electromagnetic theory. Its properties grew increasingly contrived. It had to be perfectly transparent, massless, incompressible, rigid beyond known materials, and undetectable through mechanical means. Each new requirement reduced its physical plausibility. The conceptual cost became clear. Absolute space, defined by the ether, lacked observational support. Motion relative to the ether produced no measurable effects on electromagnetic phenomena. The preferred frame receded into unobservable abstraction. This loss extended beyond optics. Classical mechanics relied implicitly on absolute space and time. Velocities referred to a fixed background. Acceleration possessed absolute meaning. The failure to detect the ether suggested that uniform motion lacked absolute significance, even for electromagnetic processes. The crisis reached beyond a single experiment. It challenged the coherence of physical law. Electromagnetism and mechanics appeared incompatible under existing assumptions. One demanded a fixed propagation speed, the other demanded additive velocities. Both enjoyed strong empirical support. Resolution required re-examining foundational concepts rather than introducing further mechanical constructs. The key step involved treating the invariance of light speed as a principle rather than an anomaly. If all inertial observers measured the same speed for light, then transformations between frames must preserve that value. Space and time would adjust accordingly. Before that reformulation emerged, the ether's failure marked a turning point. Physics relinquished the notion that space itself provided a detectable state of rest. Uniform motion lost its absolute meaning. Only relative motion between observers and events retained physical significance. The experimental evidence forced a conceptual shift. Instead of asking how fast Earth moved through space, physicists recognized that no experiment distinguished one inertial frame from another using electromagnetic signals. The laws governing light propagation applied identically across all such frames. This recognition altered the status of measurement. Distance and time measurements depended on signal exchange, constrained by light speed. Clock synchronization procedures assumed light traveled at the same speed in opposite directions. The ether hypothesis undermined this assumption while experiments supported it. The disappearance of absolute space reshaped kinematics. Simultaneity became frame-dependent. Length and time lost their universal character. These consequences followed logically once the preferred frame vanished. The ether's failure also elevated field theory. Fields no longer required mechanical substrates. They existed as fundamental entities with their own dynamics. Energy and momentum flowed through space without transport of matter. Space itself acquired physical properties encoded in constants rather than material composition. By the early 20th century, the ether survived mainly as a historical artifact. Its role as a carrier of light dissolved under experimental scrutiny. Its function as an absolute frame vanished with it. The null results did not represent experimental failure. They represented empirical guidance toward a deeper structure of reality. The loss of absolute space did not leave a vacuum. It opened the path to a new framework where invariance replaced rigidity, symmetry replaced substrate, and space-time geometry replaced mechanical scaffolding. The ether's absence became as informative as its imagined presence once had been. Through repeated null results, physics learned that light required no medium, that uniform motion possessed no electromagnetic signature, and that the structure of space and time demanded reconsideration. These lessons emerged not from philosophical argument, but from precision measurement, careful experimental design, and the refusal of nature to reveal a preferred state of rest. The emergence of special relativity followed directly from the empirical status of the speed of light as a fixed numerical constant. By the early 20th century, experiments had established that electromagnetic signals propagate in vacuum at a single speed independent of direction, source motion, or laboratory motion. This result conflicted with the kinematic structure inherited from classical mechanics, where velocities combine through simple addition and time flows uniformly for all observers. The conflict demanded resolution. Special relativity arose as that resolution, not by postulating exotic behavior, but by enforcing consistency between observed invariance and the mathematical structure of physical law. The invariance of the speed of light states that every inertial observer measures the same value for c when performing local measurements using clocks and rulers at rest relative to that observer. This statement does not privilege light as a special substance. It elevates c to a conversion factor linking temporal and spatial intervals. Once this invariance is accepted as an experimental fact, the transformation rules between inertial frames must preserve it. Classical Galilean transformations fail this requirement. Under Galilean kinematics, time coordinates remain identical across frames, while spatial coordinates shift linearly with relative velocity. Applying these transformations to wave equations alters the predicted propagation speed. A wave travelling at speed c in one frame acquires speed c plus or minus the relative velocity in another. This outcome contradicts experimental observation. The alternative involves modifying the transformation laws themselves. The new transformations must satisfy three constraints simultaneously. First, they must reduce to Galilean transformations at velocities much smaller than c. Second, they must preserve the form of physical laws, particularly the equations governing electromagnetism. Third, they must leave the speed c invariant for all inertial observers. These requirements uniquely determine the Lorentz transformations. Under these transformations, space and time coordinates mix. The time coordinate of one frame depends on both time and space coordinates of another. The spatial coordinate along the direction of relative motion depends on both space and time. The mixing coefficients depend on the relative velocity divided by c. The mathematical structure introduces a dimensionless factor commonly denoted by gamma, equal to 1 divided by the square root of 1 minus the velocity squared divided by c squared. This factor governs the deformation of time and space measurements between frames. At low velocities, gamma approaches 1. As velocity increases towards c, gamma increases without bound. Time dilation emerges directly from this structure. Consider a clock at rest in one inertial frame, marking equal intervals between ticks. Observers in a second frame moving relative to the clock assign longer time intervals between the same ticks. The dilation factor equals gamma. This effect applies universally to all physical processes, including atomic transitions, particle decays, and mechanical oscillations. It reflects a geometric property of space-time rather than a dynamical slowing caused by forces. Length contraction follows with equal necessity. A rigid rod at rest in one frame possesses a proper length defined by simultaneous position measurements at its endpoints. Observers moving relative to the rod perform simultaneous measurements in their own frame, which correspond to non-simultaneous events in the rod's rest frame. The measured length shortens by the same gamma factor along the direction of motion. This contraction ensures consistency between distance and time measurements when preserving light-speed invariance. Simultaneity itself loses universal meaning. Events simultaneous in one inertial frame occur at different times in another moving frame. This relativity of simultaneity forms a direct consequence of the invariant signal speed used to synchronize clocks. Synchronization procedures rely on exchanging light signals and assuming equal propagation speed in opposite directions. Once this assumption holds for all observers, simultaneity becomes frame-dependent. These effects combine to preserve the invariance of c. Consider a light pulse emitted from the origin of a moving frame. In that frame, the pulse expands spherically with radius equal to c multiplied by elapsed time. In another frame, moving relative to the first, spatial distances and time intervals transform such that the expanding wavefront still satisfies the same relationship between radius and time. The wavefront remains spherical, the speed remains c. This preservation reflects a deeper geometric structure. Space-time intervals combine spatial separations and temporal separations into a single invariant quantity. For light propagation, this interval equals 0. All inertial observers agree on this null condition, even while disagreeing on individual space and time components. The invariance of c thus encodes the invariance of the space-time interval. Special relativity therefore emerges as a geometric theory. It does not modify electromagnetism to fit mechanics. It modifies the kinematic framework to accommodate electromagnetic invariance. The speed limit arises because space-time geometry constrains how events connect causally. No object possessing mass can follow a null trajectory. Massive objects follow time-like paths inside the light cone, always remaining below c. Energy and momentum transform consistently within this framework. As velocity increases, kinetic energy grows faster than predicted by classical mechanics. The energy required to accelerate a massive object increases without bound as velocity approaches c. This divergence prevents massive objects from reaching or exceeding the speed of light through finite energy input. The mass-energy relationship reflects this structure. Energy equals mass multiplied by c squared in the rest frame. As velocity increases, total energy includes kinetic contributions governed by gamma. Momentum equals gamma times mass times velocity. These expressions ensure conservation laws remain valid across inertial frames while respecting the invariant speed. Relativity did not assume light speed invariance arbitrarily. The invariance entered as an empirical constraint derived from experiments. The theoretical structure followed logically. Once the invariant speed entered transformation rules, the consequences unfolded mathematically without additional assumptions. Time dilation, length contraction, and simultaneity relativity appear as necessary features rather than optional interpretations. This logical flow distinguishes special relativity from ad hoc modification. The theory preserves all verified experimental results while removing inconsistencies. It restores coherence between electromagnetism and mechanics by redefining the geometry in which both operate. The formulation achieved clarity through the work of Albert Einstein, who recognized that the conflict lay in kinematics rather than dynamics. By treating the speed of light as invariant and requiring physical laws to take the same form in all inertial frames, he derived the Lorentz transformations from first principles. The resulting framework explained existing data and predicted new effects later confirmed experimentally. Experimental validation accumulated rapidly. Measurements of fast-moving particles revealed extended lifetimes consistent with time dilation. High-energy accelerators confirmed energy-momentum relations predicted by relativistic dynamics. Precision clock comparisons aboard aircraft and satellites demonstrated time dilation directly. Each result reinforced the interpretation of c as a fundamental speed limit rooted in space-time structure. Special relativity also clarified the meaning of causality. Signals propagate at or below c. The ordering of causally connected events remains invariant across frames. Events separated by space-like intervals lack causal connection, and their temporal order depends on the observer. This distinction preserves consistency in cause and effect relationships while allowing relative simultaneity. The speed limit thus functions as a boundary between causally connected and disconnected regions of spacetime. It defines the maximum rate at which influence travels. It shapes the structure of physical law from microscopic particle interactions to macroscopic signal transmission. Within this framework, relativity appears not as a radical departure, but as a refinement forced by experiment. the universe revealed a consistent rule governing propagation. Mathematics adjusted to reflect that rule. Space and time adapted their structure accordingly. The speed of light remains invariant because space-time geometry enforces it. Attempts to exceed it encounter divergent energy requirements and causal contradictions. The limit persists across all inertial frames, all energies tested, and all known interactions. Special relativity, therefore, stands as a consequence of insisting that measured facts align with mathematical structure. The invariant speed entered physics through experiment. Geometry followed. The resulting theory preserves consistency, causality, and conservation while revealing the deep interdependence of space, time, and motion. Time dilation and length contraction arise as direct quantitative consequences of motion at speeds approaching the invariant speed c. These effects follow from the structure of space-time required to preserve a single propagation speed for all inertial observers. They represent measurable physical phenomena confirmed across multiple experimental domains, from subatomic particle behavior to precision timekeeping in orbiting laboratories. Time dilation describes the systematic difference between time intervals measured by clocks in relative motion. Consider a clock that measures time by a regular physical process, such as the oscillation of an electromagnetic transition in an atom or the decay of an unstable particle. In the clock's own rest frame, this process unfolds with a characteristic proper time. Observers moving relative to the clock measure a longer interval between the same successive events. The ratio between the measured interval and the proper interval equals the Lorentz factor, which depends only on the relative velocity divided by c. This relationship emerges from space-time geometry rather than mechanical disturbance. In relativistic kinematics, the proper time between two events equals the space-time interval along the clock's world line divided by c. For a clock in motion relative to an observer, that world line tilts through space-time. The projection of the interval onto the observer's time axis increases as velocity increases. The result reflects geometry, not interaction. The effect becomes pronounced at high velocities. At half the speed of light, the dilation factor reaches approximately 1.15. At 90% of c, the factor increases to about 2.29. As velocity approaches c, the factor grows without bound. This behavior imposes a practical limit on acceleration, since every increment in velocity requires increasing energy input for diminishing gains in speed. Length contraction complements time dilation. It affects measurements of spatial extent along the direction of motion. A rod at rest in its own frame has a proper length defined by the distance between its endpoints measured simultaneously in that frame. Observers moving relative to the rod measure its length using simultaneous position measurements in their own frame. Because simultaneity differs between frames, the endpoints correspond to different proper times along the rod. The measured length shortens by the same Lorentz factor that governs time dilation. This contraction preserves consistency between distance and time measurements. If lengths remained unchanged while time dilated, the measured speed of light would vary between frames. The paired deformation of space and time maintains the invariant ratio defining c. Both effects arise from the same transformation rules and share a common mathematical origin. These predictions yield concrete experimental consequences. One of the earliest confirmations involved unstable particles created in Earth's upper atmosphere. Muons form when cosmic rays collide with atmospheric nuclei. In their rest frame, muons possess a mean lifetime of about 2.2 microseconds. At speeds close to c, classical reasoning predicts they would decay long before reaching the surface. Observations show that large numbers reach ground-level detectors. The explanation follows directly from time dilation. In Earth's frame, muon internal clocks run slower, extending their observed lifetimes by factors consistent with relativistic predictions. Particle accelerators provide controlled environments for similar tests. beams of electrons, protons, and heavier ions circulate in storage rings at speeds exceeding 99% of c. Measurements of decay rates, synchrotron radiation emission, and beam dynamics align precisely with relativistic time dilation factors. These measurements reach precision levels exceeding 1 part in a billion. Length contraction appears indirectly in accelerator physics through momentum and energy relations. The contraction of electromagnetic field configurations around moving charges alters interaction strengths and radiation patterns. Accelerator design calculations incorporate relativistic contraction implicitly through Lorentz invariant formulations. Experimental outcomes confirm their necessity. Atomic clocks provide a direct and macroscopic demonstration of time dilation. These clocks measure time through well-defined atomic transitions, whose frequencies depend on fundamental constants. When transported at high speeds relative to Earth's surface, their accumulated time differs predictably from stationary counterparts. One of the most cited demonstrations involved flying atomic clocks aboard aircraft, travelling eastward and westward around the planet. Upon return, the airborne clocks showed time differences consistent with relativistic predictions, combining velocity-based dilation and gravitational effects. Satellite-based systems extend this confirmation continuously. Global navigation satellites orbit Earth at speeds of several kilometers per second. Their onboard clocks experience time dilation relative to ground-based clocks due to their orbital velocity. Relativistic corrections amount to microseconds per day. Without applying these corrections, positional errors would accumulate at rates of several kilometers per day. Operational accuracy confirms the theoretical framework with high precision. Length contraction appears explicitly in relativistic particle collisions. In the laboratory frame, fast-moving nuclei exhibit contracted spatial distributions along their direction of motion. This contraction increases effective interaction densities during high-energy collisions, influencing particle production rates. Experimental data from collider facilities match predictions derived from contracted geometries. These effects carry no dependence on material composition or clock mechanism. Mechanical clocks, atomic clocks, particle lifetimes, and electromagnetic oscillators all obey the same dilation rules. This universality reflects the geometric origin of the phenomena. Any physical process unfolding in time measures proper time along a world line, and that proper time transforms consistently between frames. The combined effect of time dilation and length contraction preserves causality and the invariant speed. Light pulses emitted from moving sources propagate with the same speed relative to all observers because spatial and temporal intervals adjust together. The transformation rules enforce consistency across frames without invoking hidden forces or preferred directions. The experimental record leaves little ambiguity. From subatomic scales to orbital platforms, relativistic predictions align with observation. Time dilation and length contraction operate continuously rather than discretely. Their magnitude depends smoothly on velocity, becoming negligible at everyday speeds and dominant near c. These phenomena reshape intuition while preserving physical law. Motion alters measured intervals not through mechanical distortion, but through space-time geometry. Clocks slow and distances shrink in precise mathematical relation, maintaining invariant causal structure. As velocities approach the universal speed limit, these deformations intensify, ensuring that no massive object overtakes light and that all observers agree on the fundamental ordering of events. The relationship between energy, mass, and velocity undergoes a precise and unavoidable transformation once the invariant speed c enters the structure of physical law. In relativistic physics, motion ceases to be governed by linear addition of velocities and linear growth of kinetic energy. Instead, energy, momentum, and inertia become tightly coupled through space-time geometry, producing a strict barrier that massive objects approach asymptotically without ever reaching. Massive objects follow time-like paths through space-time. Along such paths, proper time accumulates, and the space-time interval between successive events remains positive. Light, by contrast, follows null paths for which the space-time interval equals 0. This distinction divides all possible motions into fundamentally different categories. The transition from time-like to null motion would require the space-time interval along an object's world line to collapse to 0. For an object possessing non-zero rest mass, the equations governing energy and momentum prevent this transition from occurring. The quantitative expression of this constraint appears in the relativistic energy-momentum relation. Total energy relates to momentum and rest mass through a fixed geometric relationship involving c. For an object at rest, energy reduces to rest energy, proportional to mass multiplied by the square of c. As velocity increases, momentum grows, and total energy increases accordingly. The functional form ensures that energy increases faster than velocity as the latter approaches c. This behavior contrasts sharply with classical mechanics. In classical theory, kinetic energy grows proportionally to the square of velocity. Doubling velocity quadruples kinetic energy. Under this framework, nothing prevents a massive object from reaching arbitrarily high speeds given sufficient energy. Relativistic dynamics replaces this quadratic growth with a divergence. As velocity approaches c, the energy required to produce further increases rises without bound. The divergence originates from the Lorentz factor, which depends on velocity divided by c. As velocity increases, the denominator of this factor decreases, causing the factor to grow increasingly large. Every incremental increase in speed demands a larger increment in energy than the previous one. Near c, finite energy produces only infinitesimal changes in velocity. This effect introduces a natural speed limit without invoking prohibitive forces or material failure. The limit arises from the structure of space-time itself. Energy couples to motion through geometry. The closer an object moves to the null boundary defined by light propagation, the more its trajectory resembles a null path, and the more resistant it becomes to further acceleration. Inertia plays a central role in this process. In relativistic physics, inertia no longer corresponds solely to rest mass. It incorporates energy content. As kinetic energy increases, it contributes to inertia. The effective resistance to acceleration grows with velocity. This growth reflects the increasing difficulty of altering the direction of a world line as it approaches the light cone. The concept of relativistic mass once attempted to describe this behavior by assigning velocity-dependent mass to moving objects. Modern formulations avoid this terminology, instead treating mass as invariant and attributing the increased resistance to acceleration to energy-momentum geometry. The physical predictions remain the same. Acceleration diminishes as velocity increases, approaching zero as velocity approaches c under finite applied force. The asymptotic nature of the speed limit becomes clear when expressed mathematically. No finite energy input suffices to accelerate a massive object to c. Reaching c would require infinite energy. This requirement holds regardless of propulsion method, force magnitude, or duration of acceleration. The limit emerges from kinematics rather than engineering constraints. Particle accelerators provide direct empirical confirmation. Electrons accelerated to energies millions of times their rest energy achieve velocities extremely close to c. Increasing their energy further raises momentum and total energy, but produces negligible changes in speed. Measurements show that electrons at widely different energies travel at velocities differing by only parts per billion once they exceed a certain threshold. Protons exhibit similar behavior at higher energies due to their larger rest mass. In large accelerators, protons reach energies thousands of times their rest energy while remaining fractionally below c. Each additional increment of energy increases their inertia and momentum rather than their speed. The asymptotic limit remains intact. This behavior carries profound implications for propulsion, communication, and cosmology. No material object, spacecraft, or signal-carrying mass can reach or exceed the speed of light through acceleration. The barrier operates universally, independent of scale. It applies equally to subatomic particles and macroscopic bodies. Light itself occupies a distinct category. Photons possess zero invariant mass and follow null paths. Their energy relates directly to frequency rather than velocity. Increasing photon energy raises frequency while leaving speed unchanged. This property distinguishes massless excitations from massive matter fundamentally. The absence of rest mass allows photons to exist exactly on the light cone. The distinction clarifies the phrase light-speed barrier. The barrier does not obstruct motion in the manner of a wall encountered at a finite distance. Instead, it defines a boundary in space-time geometry that massive world lines approach asymptotically. Objects draw ever nearer to the boundary without crossing it. The closer they come, the more energy concentrates into inertia rather than speed. This asymptotic behavior preserves causality. If massive objects could reach or exceed c, causal order would become frame-dependent for material signals. Effects could precede causes in some inertial frames. The energy divergence prevents such trajectories from occurring, ensuring consistent temporal ordering for all causal interactions involving matter. The energy-mass relationship further explains why rest mass itself encodes enormous energy content. The factor c² acts as a conversion between mass and energy units. This factor reflects the deep connection between inertia and space-time structure. Mass represents energy bound into time-like existence. Releasing that energy alters space-time curvature and motion. Nuclear reactions illustrate this connection. Small reductions in invariant mass produce large energy releases due to the multiplication by c². These releases never propel reaction products to or beyond c. Instead, excess energy distributes among kinetic energy, radiation, and binding effects, all governed by relativistic constraints. Astrophysical phenomena reinforce the same principles. Jets emitted from active galactic nuclei and supernova remnants achieve velocities extremely close to c. Observations reveal apparent superluminal motion due to projection effects and light travel time delays, not actual superluminal speeds. Detailed modelling confirms that intrinsic velocities remain subluminal while approaching the asymptotic limit. In extreme gravitational environments such as near black holes, matter accelerates under intense curvature. Even there, locally measured velocities remain below c. General relativity preserves the same local speed limit. The geometry of space-time bends trajectories without allowing massive objects to cross the null boundary. The asymptotic nature of the barrier also shapes cosmic evolution. In the early universe, particles possessed enormous energies. Despite this, massive particles still moved at speeds below c. As the universe expanded and cooled, velocities decreased smoothly without violating relativistic constraints. The invariant speed regulated thermal histories and interaction rates. From a theoretical standpoint, the barrier emerges inevitably once invariant speed and energy conservation coexist. Any alternative framework permitting massive objects to reach CE would require abandoning either energy conservation or causal structure. Such frameworks conflict with experimental evidence across scales. The distinction between massless and massive excitations extends into quantum field theory. Fields associated with massive particles exhibit dispersion relations that curve in energy-momentum space, enforcing subluminal group velocities. Massless fields exhibit linear dispersion, producing propagation exactly at c. The geometry of these relations encodes the same asymptotic behavior seen in classical relativistic mechanics. The light-speed barrier thus reflects a deep architectural feature of reality. It separates categories of existence rather than imposing a mechanical constraint. Matter occupies the interior of the light cone. Radiation traces its surface. The boundary remains mathematically sharp and physically unattainable for massive entities. This understanding reframes acceleration limits. Engines and forces do not fail at sea. Space-time geometry absorbs energy into inertia. The notion of hitting the speed of light dissolves. Motion approaches a limit defined by geometry, not resistance. In this framework, the speed of light acts as an organizing constant linking mass, energy, and motion. It converts between units, constrains trajectories, and preserves causality. The barrier appears not as an obstacle but as a boundary condition encoded into the structure of space-time itself. The connection between the speed of light and causality emerges directly from the geometric structure of space-time. Once a single invariant speed governs the propagation of all physical influences, that speed divides space-time into distinct regions with sharply different causal properties. These regions determine which events can influence which others and in what temporal order. Faster-than-light motion disrupts this structure in a precise, quantifiable way, threatening the logical consistency of cause and effect, rather than merely challenging technological feasibility. Space-time in relativistic physics is represented as a four-dimensional continuum combining three spatial dimensions with one temporal dimension. Events occupy points in this continuum. The separation between two events is described not by distance or time alone, but by a space-time interval that combines both using the constant c as a conversion factor. This interval determines whether one event can causally influence another. For any given event, space-time divides into three categories. Events that can be influenced by the given event form its future causal region. Events that could have influenced it form its past causal region. Events lying outside both regions possess space-like separation and admit no causal connection. The boundaries separating these regions are defined by light propagation. These boundaries form geometric surfaces called light cones. The future light cone consists of all events reachable by signals travelling at or below the speed of light after the given event. The past light cone consists of all events from which such signals could have reached the given event. The interior of the light cone corresponds to time-like separations, accessible to massive particles moving below c. The surface of the light cone corresponds to null separations, traced by massless signals such as light itself. This structure does not arise from convention. It emerges from the invariant speed c and the Lorentz transformations that preserve it. Every inertial observer agrees on the shape of light cones, even while disagreeing on spatial distances and time intervals. The classification of separations into time-like, space-like, and null remains invariant across frames. Causality follows directly. A cause must precede its effect in every inertial frame. This requirement holds automatically for events connected by time-like or null intervals. If one event lies within the future light cone of another, all observers agree that the cause occurs before the effect. The temporal ordering remains invariant. No observer can reverse it through a change of reference frame. Space-like separated events behave differently. Their temporal order depends on the observer's state of motion. One inertial frame may assign event A as occurring before event B, while another assigns the reverse. Because no signal travelling at or below c can connect such events, this ambiguity poses no physical problem. No causal influence links them, so order carries no operational meaning. Faster-than-light motion alters this classification. A signal propagating faster than c would follow a space-like trajectory rather than a time-like or null one. Such a trajectory lies outside the light cone. Once such trajectories exist, events that were previously causally disconnected become connectable. This connection introduces frame-dependent temporal ordering into causal chains. The problem appears immediately when combining faster-than-light propagation with the relativity of simultaneity. Because different inertial frames disagree on which events are simultaneous, a superluminal signal sent from one event to another can arrive before it is sent according to some observers. This inversion arises from the geometry of space-time rather than from measurement error. A concrete scenario illustrates the issue. Consider two observers moving relative to one another. In the rest frame of the sender, a faster-than-light signal travels from event A to event B. In another inertial frame moving relative to the first, the Lorentz transformation mixes time and space coordinates such that event B occurs earlier than event A. The signal appears to propagate backward in time. This inversion becomes physically problematic when combined with bidirectional communication. If the receiver responds with another faster-than-light signal, the return signal can arrive at the sender before the original transmission occurred. This configuration creates a closed causal loop. An effect influences its own cause. Such loops undermine the logical structure of physical law. They permit contradictions. A message could instruct its own sender not to send it. Physical predictions lose consistency. Deterministic evolution breaks down. Probability assignments lose coherence. These contradictions do not depend on exotic assumptions. They follow directly from Lorentz symmetry and faster-than-light propagation, any theory preserving relativistic space-time structure while allowing superluminal signals encounters these causal paradoxes. The speed of light therefore functions as a causal speed limit. It bounds not only the transmission of matter and energy, but the transmission of influence itself. By restricting all causal signals to time-like or null paths, space-time geometry preserves consistent temporal ordering for all causal chains. This role extends beyond electromagnetism. Gravitational interactions propagate at the same invariant speed. Changes in gravitational fields travel along null or time-like trajectories determined by space-time curvature. Observations of gravitational waves confirm that their arrival times match those of electromagnetic counterparts to high precision, reinforcing a single causal speed. Quantum theory introduces correlations that appear non-local, yet these correlations do not violate causal structure. Entangled systems exhibit statistical relationships across space-like separations, but no controllable signal propagates faster than c. Measurement outcomes remain locally random. The formalism enforces this through operator commutation relations that vanish outside the light cone. Observable effects respect relativistic causality. The geometry of light cones thus underwrites both classical and quantum consistency. It defines domains of dependence for physical laws. Field equations remain hyperbolic, ensuring finite propagation speeds. Initial conditions specified on a space-like surface determine evolution within the future light cone of that surface. This structure also governs determinism. Predictability operates within causal domains. Events outside a light cone remain inaccessible until signals arrive. The speed limit preserves locality, preventing instantaneous action at a distance in the operational sense. The causal role of C becomes clearer when considering alternative geometries. If no invariant speed existed, causal regions would lack sharp boundaries. Signals could propagate arbitrarily fast, erasing the distinction between space-like and time-like separation. Temporal order would become frame-dependent even for interacting events. Physical law would lose coherence. If multiple invariant speeds existed, causal structure would fragment. Different interactions would possess different light cones, producing nested or intersecting causal regions. Such structures would complicate conservation laws and undermine the universality of simultaneity conventions. Observations offer no evidence for such behavior. The existence of a single invariant speed produces a clean geometric partition. All interactions share the same causal cones. The structure remains simple, consistent, and experimentally supported. Historically, the geometric interpretation of causality matured through the work of Hermann Minkowski, who reformulated special relativity in geometric terms. In this formulation, spacetime becomes a four-dimensional manifold with a metric signature distinguishing time from space. Light cones emerge naturally from this metric. Causality becomes a property of geometry rather than an added rule. In this view, physical laws describe how world lines curve and how fields propagate within the allowed causal structure. Forces alter trajectories but never permit them to exit the light cone. Acceleration changes direction within spacetime without violating causal boundaries. General relativity extends this structure to curved spacetime. Gravity alters the shape of light cones locally by curving spacetime. Even so, the local causal structure remains intact. At each point, light cones define permissible directions of influence. Curvature tilts and distorts cones without eliminating them. Faster-than-light local motion remains forbidden. Event horizons illustrate extreme causal geometry. Near a black hole, light cones tip inward such that all future directed paths lead toward the singularity. Signals emitted within the horizon cannot reach distant observers. This behavior reflects geometry rather than force. Causality follows space-time structure even under extreme curvature. Cosmology exhibits similar effects. In expanding space-time, light cones stretch and tilt due to cosmic expansion. Particle horizons define limits on causal contact in the universe. Regions beyond these horizons remain causally disconnected at a given cosmic time. The speed of light governs the growth of these horizons. Causality therefore appears not as an abstract principle imposed on physics, but as a geometric fact encoded in spacetime itself. The invariant speed c defines the slope of light cones in spacetime diagrams. This slope determines which events can influence which others. Faster-than-light propagation would alter that slope, reshaping causal regions and permitting contradictions. The preservation of causality constrains physical theory strongly. Any proposed extension of physics must respect light cone structure or replace it with an alternative that avoids paradox. The empirical success of relativity and quantum field theory indicates that the existing structure suffices across tested regimes. The speed of light thus occupies a foundational role. It links measurement, motion, and causality into a single framework. It ensures that causes precede effects consistently for all observers. It divides spacetime into accessible and inaccessible regions in a precise, invariant way. Within this framework, causality does not emerge from dynamics alone. It arises from geometry. The speed limit defines the shape of spacetime itself. Once that shape is fixed, cause and effect follow inevitably. Photons occupy a singular position in relativistic physics because their motion lies exactly on the boundary that separates all possible time-like motions from those that are forbidden. They propagate at the invariant speed c in every inertial frame, and this fact carries precise consequences for how time, reference frames, and observation are defined. Understanding why light does not experience time requires examining proper time, space-time intervals, and the mathematical limits imposed by Lorentz geometry. Proper time represents the time measured by a clock that travels along a specific world line. It corresponds to the space-time interval accumulated along that path, scaled by the invariant speed c. For objects with mass, this quantity is always positive. Their world lines lie inside the light cone, and as they move through spacetime, proper time advances steadily. Every physical process internal to such an object, atomic transitions, biochemical reactions, mechanical oscillations, unfolds according to this accumulated proper time. photons differ fundamentally. Their world lines trace null paths, also called light-like trajectories. Along such paths, the space-time interval equals 0. When the interval vanishes, proper time does not accumulate. This result follows directly from the geometry of space-time, rather than from an assumption about consciousness or perception. The mathematical definition of proper time assigns 0 duration to null separations. This property does not imply that photons experience time in a psychological sense. It reflects the absence of a rest frame and the geometric nature of space-time. Proper time is defined operationally. It is what a clock measures when carried along a trajectory. No clock can be attached to a photon. The equations describing clocks require time-like world lines. Null world lines admit no internal time parameter. The statement that light does not experience time therefore means that the emission and absorption of a photon occur at the same value of proper time along the photon's path. From the perspective of space-time geometry, these events connect directly without temporal separation. This conclusion holds regardless of the spatial distance between emission and absorption, as measured in any inertial frame. The result contrasts sharply with how observers describe photon motion. In any inertial frame, a photon travels at speed c and requires a finite coordinate time to traverse a finite distance. That coordinate time depends on the observer's frame of reference. Different observers assign different travel times and distances to the same photon. Yet all agree that the space-time interval along the photon's path remains 0. This invariance underscores the distinction between coordinate time and proper time. Coordinate time depends on the chosen reference frame. Proper time depends only on the geometry of the world line. For massive objects, the two relate through the Lorentz factor. For photons, the relation degenerates. The Lorentz factor diverges as velocity approaches c, and proper time collapses to 0. The divergence signals a limit rather than a physical process. It indicates that no inertial reference frame exists in which a photon remains at rest. Attempting to construct such a frame leads to mathematical inconsistencies. The Lorentz transformation that would bring an observer into the photon's rest frame would require infinite boost velocity and infinite energy. The transformation coefficients diverge. The coordinate axes lose meaning. This limit defines a boundary of physical description. Inertial frames apply only to observers moving at speeds less than c relative to one another. The framework of special relativity excludes reference frames travelling at c. This exclusion does not represent an oversight. It reflects the structure of space-time. Frames at c lie outside the domain of Lorentz transformations. Because no rest frame exists for light, concepts that rely on rest frames lose applicability. Length contraction and time dilation relate measurements between inertial frames. For photons, these concepts reach singular limits. Length contraction along the direction of motion approaches 0. Time dilation approaches infinity. These limits signal the breakdown of frame-based interpretation rather than physical compression or freezing. The absence of proper time along null paths influences how light interacts with matter. Absorption and emission occur at specific space-time events governed by interactions between fields and charges. From the emitter's frame, emission occurs at one time. From the absorber's frame, absorption occurs at another. Along the photon's trajectory, no intermediate temporal structure exists. The interaction connects two events directly in space-time geometry. This feature explains why photons retain phase coherence over vast distances. Phase evolution relates to coordinate time in a given frame, yet the invariant structure ensures consistent interference effects across frames. The photon's propagation does not involve internal aging or decay. Its properties remain unchanged, except through interactions with fields or matter. The concept of proper time also clarifies why light serves as a universal clock signal despite lacking its own clock. Light defines simultaneity conventions. Observers synchronize clocks by exchanging light pulses and assuming equal propagation speed in opposite directions. This procedure relies on the invariant null structure of space-time. The absence of proper time for light does not undermine this role. It enables it. The boundary imposed by null motion also constrains observation. Observers receive information through light signals. The finite speed of light introduces delays that depend on distance and relative motion. Because photons carry no proper time, all temporal structure arises from the observer's frame and the geometry of space-time between events. Observational horizons emerge naturally from this structure. In cosmology, this principle defines particle horizons. Light emitted from distant regions reaches observers only if sufficient coordinate time has elapsed since emission. The photon itself does not age during transit. The separation arises entirely from space-time expansion and observer motion. This distinction matters when interpreting redshift, cosmic microwave background radiation, and horizon scales. The absence of a photon rest frame also clarifies why assigning a photon perspective leads to conceptual confusion. Phrases such as, "from the photon's point of view," lack physical meaning. Point of view implies a reference frame with clocks and rulers. Photons admit no such frame. Any attempt to describe what a photon sees replaces geometry with metaphor. This limitation protects consistency. If a photon possessed a rest frame, one could define simultaneity along its path. That simultaneity would conflict with all inertial frames related by Lorentz transformations. Causal structure would fracture. The prohibition of null frames preserves coherence. The same reasoning applies to other massless excitations. Gravitational waves propagate along null trajectories. They also accumulate no proper time along their paths. Their emission and detection connect directly in space-time geometry. The equivalence of light and gravitational wave propagation speeds reflects this shared null structure. Quantum field theory incorporates these facts at a foundational level. Field operators propagate influences through commutators that vanish outside the light cone. For massless fields, propagation occurs exactly on the cone. The lack of proper time does not eliminate dynamics. It constrains where dynamics occur. Evolution unfolds with respect to coordinate time in chosen frames while respecting invariant null structure. The energy of a photon relates to frequency rather than velocity. Frequency transforms under Lorentz boosts through Doppler effects. Different observers measure different frequencies for the same photon depending on relative motion. These differences reflect how coordinate time intervals project onto the photon's null world line. Proper time remains absent. This framework explains why increasing photon energy does not alter its speed. Speed remains fixed at c. Energy increases through higher frequency, corresponding to tighter oscillations in coordinate time. The geometric path remains unchanged. The null condition persists. The boundary between timelike and null motion also influences how matter approaches the speed of light. As massive particles accelerate, their world lines tilt closer to the light cone. Proper time accumulation per unit coordinate time decreases. Internal clocks slow relative to external frames. At the limit, proper time would vanish, mirroring photon behavior. The infinite energy requirement prevents reaching that limit. This convergence highlights continuity within spacetime geometry. Massive and massless motions differ in degree rather than in kind until the null boundary intervenes. The boundary remains unreachable for matter, preserving distinct categories of motion. Observation itself depends on null structure. Signals arriving simultaneously at an observer define events on the observer's past light cone. All information accessible at a given moment lies on that cone. Events inside the cone belong to the past. Events outside remain inaccessible. The geometry organizes knowledge itself. The meaning of proper time thus extends beyond clocks. It defines what it means for an object to persist through time. Objects with mass trace histories with duration. Light traces connections without duration. Both roles remain essential. Matter experiences time. Light structures time. This division does not privilege observers over photons. It reflects different geometric roles within the same spacetime. Observers exist within time-like trajectories. Photons connect those trajectories. Proper time accumulates for one and vanishes for the other. The combination produces a coherent causal network. Attempts to quantize spacetime or modify relativity at extreme scales must respect this structure or replace it consistently. Many speculative theories explore altered dispersion relations or emergent spacetime. Yet recoverable low-energy behavior consistently restores null propagation for massless fields and time-like propagation for massive ones. The distinction persists. The conceptual boundary imposed by null motion therefore represents a fundamental limit of description. It delineates where reference frames apply, where clocks operate, and where geometric relations suffice. Light does not experience time because time, as measured by clocks, applies only to trajectories with proper duration. Light defines the boundary of that domain. Within this boundary, observation, causality, and measurement interlock. The invariant speed c shapes spacetime into a structure where some paths possess duration and others connect events directly. Photons inhabit the latter class. Their role anchors the geometry that allows all other physical processes to unfold consistently. Light propagates through vacuum and through material media in ways that share a common geometric foundation, yet differ profoundly in physical mechanism. In vacuum, electromagnetic disturbances propagate at the invariant speed c, fixed by the structure of spacetime and the constants of electromagnetism. In matter, measured light speeds fall below this value, sometimes dramatically so. This reduction does not reflect a fundamental slowing of light itself. It arises from collective interactions between the electromagnetic field and charged constituents of matter, governed by microscopic dynamics that preserve relativistic causality at every stage. In vacuum, Maxwell's equations reduce to wave equations whose solutions propagate at a single characteristic speed determined by the electric permittivity and magnetic permeability of free space. No charges or currents intervene. The field evolves freely. Energy, momentum, and information propagate along null trajectories. The speed c appears as a structural constant rather than a dynamical variable. Introducing matter alters the situation by adding charged particles capable of responding to electromagnetic fields. Atoms and molecules contain bound electrons, whose motion couples to applied electric fields. When an electromagnetic wave enters a material, its oscillating electric field exerts forces on these charges. The charges accelerate, producing secondary electromagnetic radiation. The resulting field inside the medium equals the superposition of the incident field and the fields re-emitted by the charges. This interaction does not resemble light simply moving slower between collisions. Instead, it constitutes a continuous collective response. The electromagnetic wave induces polarization in the medium. Dipole moments form as electrons shift relative to nuclei. These dipoles oscillate at the driving frequency of the wave and radiate. The re-radiated field interferes with the original field, modifying the phase evolution of the combined wave. The macroscopic effect appears as a change in phase velocity. The wavefront advances more slowly through the medium than it would in vacuum. The ratio between the vacuum speed c and the phase velocity defines the refractive index of the material. A refractive index greater than 1 corresponds to reduced phase velocity. This description rests on averaging over enormous numbers of microscopic interactions. A single photon interacting with matter does not literally slow down and speed up between collisions in a classical sense. In quantum electrodynamics, photon propagation through a medium involves repeated absorption and re-emission processes, along with virtual excitations of electronic states. The effective propagation speed emerges from the cumulative phase delay introduced by these interactions. Crucially, the fundamental interactions respect relativistic constraints. Each absorption and emission event occurs locally. The electromagnetic influence propagates between atoms at speed c. No individual interaction transmits influence faster than the invariant speed. The apparent slowing arises from the temporal structure of the response, not from superluminal or subluminal propagation of fundamental signals. The refractive index encodes this structure quantitatively. It depends on the density of charge carriers, their binding strengths, and the frequency of the incident light. At frequencies far below electronic resonance frequencies, electrons respond elastically, producing modest refractive indices. Near resonances, response becomes strong and dispersive, producing rapid variation of refractive index with frequency. Dispersion reflects the frequency dependence of the medium's polarization response. Different frequency components of a wave packet propagate with different phase velocities. This behavior leads to pulse spreading and reshaping. The group velocity, which governs the propagation of wave packet envelopes, may differ from the phase velocity. In some regimes, group velocity falls well below c. In others, it may exceed c or even become negative without violating causality. These counterintuitive cases require careful interpretation. Group velocity does not represent the speed of information transfer in all circumstances. It reflects how the peak of a wave packet moves, which can be influenced by reshaping effects. The speed at which a genuinely new disturbance or signal front propagates remains bounded by c. This front velocity, associated with the earliest non-zero response of a system, never exceeds the invariant speed. The distinction preserves relativistic causality. Even in materials engineered to produce unusual dispersion, no signal carrying new information arrives before a light-speed-limited causal influence. Experiments demonstrating superluminal group velocities confirm this constraint explicitly. Signal fronts respect light cone structure. The slowing of light in matter therefore does not contradict relativity. Relativity constrains fundamental signal propagation and causal influence. It does not require that phase or group velocities in media equal c. The invariant speed applies to local propagation in vacuum and to the ultimate causal limit. This distinction becomes clearer when considering how refractive indices arise from atomic properties. In a simple classical model, electrons bound to atoms behave like driven oscillators. The electric field of the light wave displaces electrons, creating oscillating dipoles. The re-radiated field lags behind the driving field due to inertia and binding forces. This lag introduces a phase shift proportional to frequency and material parameters. Summing over all dipoles yields a macroscopic polarization field. Maxwell's equations incorporate this polarization through modified constitutive relations linking electric displacement to electric field. The resulting wave equation predicts a reduced phase velocity. No assumption of altered spacetime structure enters the derivation. The geometry remains Minkowskian. Only the material response modifies propagation. Quantum theory refines this picture. Electronic states possess discrete energy levels. Photons interact with these states through absorption and emission processes governed by selection rules and coupling strengths. Virtual excitations contribute to refractive behavior even when photon energies fall below real transition energies. These virtual processes introduce phase shifts without net energy transfer. The cumulative effect remains local and causal. Each interaction respects relativistic constraints. The apparent macroscopic delay reflects the sum of many microscopic delays, each bounded by local dynamics. The invariant speed governs the propagation between interaction sites. The difference between vacuum and medium propagation highlights the role of collective behavior in physics. Vacuum propagation reveals fundamental structure. Medium propagation reveals emergent phenomena arising from complex, many-body systems. The distinction mirrors that between fundamental constants and effective parameters. The refractive index itself lacks universality. It varies with material composition, temperature, pressure, and frequency. It can exceed 1, drop below 1 in certain frequency ranges, or approach unity as frequency increases far beyond resonances. In the limit of extremely high photon energy, materials become transparent and refractive indices approach 1. Propagation tends toward vacuum behavior. This convergence reinforces the interpretation that reduced light speed in matter does not represent a modification of fundamental law. It reflects interaction strength. When interactions weaken, propagation approaches c. Relativistic invariance remains intact throughout. Observers in different inertial frames agree on the causal ordering of events associated with light propagation in media. They may disagree on phase velocities or frequencies due to Doppler effects, but causal structure persists. The light cone remains the same. The existence of slower effective propagation also explains everyday optical phenomena. Refraction at interfaces arises because wave fronts change direction when entering materials with different refractive indices. The geometry of wave propagation changes due to altered phase velocity. Snell's law follows from boundary conditions and phase continuity. These phenomena operate entirely within relativistic constraints. Optical fibers exploit controlled refractive index profiles to guide light. Total internal reflection confines propagation. The signal travels at speeds below c due to the material response. Timing calculations for fiber optic communication account for this reduced speed. No fundamental constraint is violated. The same principles govern extreme cases such as slow light experiments, where group velocities are reduced to meters per second or less. These experiments involve strong dispersion near atomic resonances. Light pulses become spatially compressed and temporally stretched within the medium. The underlying electromagnetic interactions remain local and causal. When the medium is removed or the interaction switched off, propagation resumes at c. Even more striking, light pulses can be temporarily stored in atomic ensembles and later released. During storage, electromagnetic energy transfers into collective atomic excitations. No propagation occurs during storage. When re-emitted, the pulse continues. Throughout, causal structure remains respected. Information does not jump across space-time instantaneously. The vacuum remains unique. In the absence of matter, no polarization response exists to delay phase evolution. The electromagnetic field propagates freely at c. This behavior defines the invariant speed used to construct space-time geometry. Media introduce effective delays without altering geometry. This distinction clarifies why relativity remains compatible with materials exhibiting refractive indices greater than 1. Relativity constrains the transformation properties of physical laws and the maximum speed of causal influence. It does not constrain emergent collective parameters in matter. The same reasoning applies to other fields. Sound propagates at speeds far below c due to the inertia and compressibility of matter. No one interprets this as a violation of relativity. Sound waves involve mechanical interactions mediated by electromagnetic forces at the atomic level. Those interactions propagate at c. The emergent wave speed reflects collective dynamics. Light in matter represents an intermediate case. It involves electromagnetic fields directly, yet still interacts with matter. The resulting propagation speed reflects the balance between field dynamics and material response. Understanding this balance resolves common misconceptions. Statements that light slows down in glass suggest a naive picture of photons breaking between atoms. The correct picture involves continuous field interaction, phase delay, and re-emission. The invariant speed remains untouched. The distinction also matters for interpreting experiments involving apparent superluminal effects. In dispersive media, group velocities can exceed c without transmitting information superluminally. The earliest detectable response remains constrained by light cone structure. Relativity governs causality, not the motion of wave peaks. In modern physics, this understanding extends to metamaterials engineered to produce exotic optical properties. Negative refractive indices, anomalous dispersion, and tailored phase responses emerge from structured materials. These phenomena manipulate effective propagation while respecting fundamental limits. No experiment has demonstrated causal influence exceeding c. The robustness of this structure reflects deep consistency. Relativity constrains local interactions. Material properties emerge from those interactions. Effective propagation parameters inherit constraints implicitly. Thus, the contrast between light in vacuum and light in matter reveals the layered nature of physical law. At the deepest level, invariant speed and space-time geometry govern causal structure. At emergent levels, collective interactions modify effective behavior without altering fundamentals. Light slows in matter because matter responds. Light does not slow fundamentally because space-time does not permit it. The invariant speed remains the organizing principle. All deviations arise from interaction, not from altered geometry. This understanding unifies optics, electromagnetism, quantum theory, and relativity into a coherent picture. Vacuum propagation defines limits. Matter introduces complexity. Causality remains intact throughout. Quantum field theory describes nature in terms of fields that extend through space-time, with particles appearing as quantized excitations of those fields. In this framework, the speed limit c is encoded at the deepest level in the mathematical structure that determines how influences propagate and how measurements relate across space-time. Vacuum fluctuations, virtual particles, and entanglement often sound like mechanisms for instantaneous action at a distance, yet the formalism enforces causal propagation with exceptional rigidity. A quantum field assigns an operator to every space-time point. These operators create and annihilate excitations, and their algebra determines what kinds of correlations and causal influences can occur. The key requirement is locality. Interactions occur through products of fields evaluated at the same space-time point, and the dynamics is generated by a Hamiltonian or Lagrangian density built from local terms. Locality alone does not automatically enforce a speed limit, because one could imagine local equations that still permit arbitrarily fast propagation. The speed limit enters because relativistic quantum field theory is constructed to be compatible with Lorentz invariance, which carries the invariant null structure defined by C. The propagation of disturbances is governed by Green's functions or propagators, which describe how an excitation created at one spacetime point contributes to amplitudes at another. For a relativistic field, the propagator structure reflects the light cone geometry. Singular support and causal response align with null and time-like separations. The sharpest statement comes from microcausality. For observables built from fields, the commutator of two local operators evaluated at space-like separated points vanishes. This vanishing commutator expresses operational independence. Measurements performed in regions separated by space-like intervals do not influence one another, and changing an experimental choice in one region does not change outcome statistics in the other region at that time. The speed c enters through the definition of space-like separation, which is a geometric classification that every inertial observer agrees on. Vacuum fluctuations appear because the lowest energy state of a quantum field is not a classical zero. The vacuum contains non-zero variance in field amplitudes. These fluctuations manifest in measurable effects such as the Lamb shift, spontaneous emission, and the Casimir force between conductors at small separations. The language of virtual particles popping in and out provides an intuitive shorthand for internal lines in perturbation theory, yet the underlying object is the vacuum correlation function of fields. These correlations extend over space-like separations, meaning the vacuum state exhibits statistical structure across regions outside one another's light cones. This fact often creates confusion about signal speed. Vacuum correlations exist at space-like separation, and they can be strong enough to produce measurable consequences when integrated over time or when boundaries are present. The key distinction is between correlation and controllable influence. Correlations describe joint statistics for outcomes in different regions under fixed measurement settings. Signaling requires that choices made in one region change the marginal outcome distribution in the other region. Relativistic quantum field theory prohibits such changes at space-like separation because microcausality enforces commutation of observables there, and the dynamics preserves that commutation structure. Virtual particles arise in perturbative calculations as intermediate states that do not satisfy the classical on-shell energy-momentum relation. In Feynman diagrams, internal lines correspond to propagators integrated over all possible four momenta, including values that would correspond to superluminal phase features in naive interpretations. These internal contributions do not represent physical particles travelling faster than c. They are components of an amplitude, and only the full gauge-invariant, causality-respecting sum of contributions corresponds to observable probabilities. The speed limit applies to physical signal propagation and to causal response functions, not to intermediate mathematical decompositions of an amplitude. The distinction becomes precise by separating time-ordered propagators from causal propagators. The Feynman propagator is a time-ordered object useful for perturbation theory, and it has support outside the light cone in a distributional sense. This does not violate causality because it is not itself a measurable signal response function. The retarded propagator, which governs causal response to a source switched on at a given time, vanishes outside the future light cone. If a localized external current drives the electromagnetic field, the resulting field at a distant point changes only after a delay consistent with light cone propagation. The mathematical object that enforces this is the retarded Green's function, and its support is confined to time-like and null separations. This causal confinement persists in interacting theories. Interactions dress propagators and create non-trivial dispersion relations in media, yet the fundamental causal structure remains encoded in commutators and in the analytic properties of correlation functions. The Kramers-Kronig relations in linear response theory link dispersion to absorption through causality. The response at a given time depends only on earlier times, and this constraint appears as specific analyticity conditions in frequency space. The same analytic structure ensures that fronts and causal disturbances respect the light cone, even when group velocities vary. Entanglement brings the issue into sharp focus because it produces correlations that violate classical intuitions about separability. Two systems prepared in an entangled state exhibit measurement outcomes that are statistically linked even when separated by space-like intervals. Experiments demonstrate these correlations with high significance. The correlations appear immediately when outcomes are compared, and they remain consistent with quantum predictions regardless of separation distance. The no-signaling constraint clarifies what this implies. If one observer measures one half of an entangled pair with a chosen setting and another observer measures the other half with a chosen setting, the joint distribution depends on both settings, yet the marginal distribution for either observer alone does not depend on the distant setting. The local outcome statistics remain fixed. This property means that entanglement cannot be used to transmit a message faster than c. The correlations become usable information only when classical communication, limited by c, brings the datasets together for comparison. In quantum field theory, entanglement is not a special add-on. The vacuum itself is entangled across spatial regions. If space-time is partitioned into two regions, the vacuum state restricted to one region appears mixed because of entanglement with the other region. This structure underlies phenomena such as the Unruh effect and the thermal character of horizon-restricted states. Even in these cases, operational signaling remains light cone limited. Horizon thermality does not permit superluminal communication. It reflects how different observers decompose field modes, while the causal structure remains anchored to null geometry. The speed limit also appears in the way quantum measurements are modelled. Measurement interactions are physical processes mediated by fields. A detector couples locally to a field in its immediate vicinity. The detector's excitation probability depends on the field's correlation function along the detector's world line, integrating over proper time. Changing a distant experimental arrangement modifies field correlations in a global description, yet it does not create a causal disturbance at the detector before signals can propagate there. Any change in detector statistics that could be used for signaling would require a non-zero commutator between relevant observables at space-like separation, which microcausality forbids. Another route to the same conclusion comes from relativistic energy-momentum constraints. Physical particles with non-zero invariant mass satisfy dispersion relations that keep group velocities below c in vacuum. Massless particles satisfy linear dispersion with group velocity equal to c. Interactions can modify effective dispersion in media, yet causal front propagation remains bounded. In vacuum, a localized wave packet for a relativistic field evolves so that its support outside the light cone remains exponentially suppressed or purely distributional in ways that cannot carry a controllable signal. The earliest detectable change driven by a localized source appears on or inside the future light cone. The subtlety arises because quantum mechanics assigns amplitudes rather than classical trajectories. A wave function or field excitation can have tails, and in some mathematical representations, those tails extend to space-like separations. The operational question is whether those tails allow a receiver to distinguish, with any measurement protocol, whether a sender performed one action or another before a light-speed signal could arrive. The structure of relativistic quantum theory prevents such distinguishability. The receiver's reduced density matrix remains unchanged under distant unitary operations at space-like separation, preserving no signaling. Vacuum fluctuations also interact with boundaries and external fields in ways that produce forces and energy shifts. The Casimir effect, for instance, can be computed as a change in vacuum mode structure between conducting plates. The resulting force depends on plate separation and geometry, and it is often described as arising from altered vacuum fluctuations between plates versus outside. This effect does not transmit signals faster than c. Changing the plate configuration in one region cannot instantaneously alter measurable outcomes in a space-like separated region because electromagnetic influence still propagates through causal fields. Any rearrangement sends radiation and stress changes outward at c. The same causal discipline governs renormalization and ultraviolet physics. Virtual processes at very short distances contribute to measurable quantities, yet the renormalized theory preserves locality and Lorentz invariance in its low-energy predictions. Divergences are handled through consistent regularization and renormalization schemes that preserve symmetries, including causal structure. The resulting effective field theories maintain light cone-limited propagation even when high-energy modes are integrated out. Signal speed constraints become especially clear in scattering. In relativistic scattering, the S-matrix links asymptotic in-states and out-states defined at early and late times. The locality of interactions implies cluster decomposition. Widely separated experiments yield independent outcomes. Violations of causal structure would spoil this property and lead to observable inconsistencies. The empirical success of relativistic scattering predictions across particle physics supports the causal framework to extreme precision. Quantum mechanics respects IC because the relativistic version of the theory is built so that observable operations in space-like separated regions commute. Causal response functions have support only in the future light cone, and the transformation rules between inertial frames preserve the null structure defined by C. Vacuum fluctuations and virtual particles represent internal correlations and intermediate contributions within amplitudes, while information transfer remains governed by operational distinguishability, which remains constrained by light cone geometry. Entanglement produces correlations that exceed classical bounds, while no signaling preserves causal order by preventing controllable influence from propagating outside the light cone. Gravity alters the paths that light follows without altering the local speed at which light propagates. This statement captures a central feature of general relativity. Gravitation does not act as a force that pushes or pulls light in the Newtonian sense, nor does it slow light down in the way matter does. Instead, gravity reshapes space-time itself, and light follows the geometry of that space-time exactly. Understanding this requires abandoning the idea of gravity as a force acting within space and replacing it with curvature of space-time as the fundamental description. In general relativity, space-time is represented as a four-dimensional manifold equipped with a metric that defines distances and time intervals. Matter and energy determine the form of this metric through field equations that relate curvature to the stress-energy content of the universe. Once the metric is fixed, it determines how objects move. Massive objects follow time-like geodesics, which are paths that locally maximize proper time. Light follows null geodesics, which are paths for which the space-time interval remains exactly zero. The key point is that geodesics are not defined by forces or accelerations. They are defined by geometry. A geodesic is the straightest possible path in a curved space-time, even though it may appear curved when projected into three-dimensional space. Light bends near massive objects because space-time itself is curved in their vicinity, not because gravity exerts a force on photons. Locally, the speed of light remains exactly c. At every space-time point, it is always possible to choose a sufficiently small region where space-time appears flat to an excellent approximation. In that local inertial frame, the laws of special relativity apply, and light propagates at c in all directions. This local statement holds everywhere, including near massive bodies, and even arbitrarily close to black hole horizons. Any apparent change in light speed arises only when comparing measurements made at different locations or using global coordinate systems. The bending of light was one of the earliest empirical confirmations of general relativity. When light passes near a massive body such as the Sun, its path curves. This effect can be calculated by determining the null geodesics of the space-time metric produced by the Sun's mass. The resulting deflection angle depends on the mass and the closest approach distance. Observations of starlight during solar eclipses confirmed this prediction with increasing precision over the 20th century. The mechanism behind this bending can be understood by examining how space-time geometry modifies distances and times. Near a massive object, spatial distances and temporal intervals differ from their flat space-time counterparts. Light always travels along paths that keep the space-time interval zero, but the projection of those paths into ordinary space appears curved. The curvature reflects the fact that straight lines in curved geometry do not remain straight when viewed from an external perspective. Another manifestation of gravitational influence on light is gravitational redshift. Light climbing out of a gravitational potential well loses energy, as measured by distant observers, resulting in a decrease in frequency. Locally, however, the light still travels at c. The change in frequency arises from differences in clock rates at different gravitational potentials, not from a change in propagation speed. Clocks deeper in a gravitational field run more slowly relative to clocks farther away. When light is emitted from the deeper region, its frequency reflects the slower ticking of the emitter's clock. This distinction between local and global descriptions is essential. Coordinate speeds of light can vary in curved spacetime when expressed in certain coordinate systems. For example, in coordinates adapted to a distant observer, the radial coordinate speed of light near a black hole appears to decrease as the horizon is approached. This effect does not represent a physical slowing of light. It reflects how the chosen coordinates slice spacetime. Any local observer measuring light passing by will still obtain C. Null geodesics provide the precise mathematical description of light propagation in curved spacetime. A null geodesic satisfies the condition that the spacetime interval along the path remains zero, and it extremises the path in a way analogous to straight lines in flat space. Solving for null geodesics in a given metric yields predictions for light bending, time delays, lensing, and horizon behaviour. Gravitational lensing offers a striking large-scale example. Massive objects such as galaxies and clusters curve spacetime over vast regions. Light from distant sources follows null geodesics through this curved geometry, producing multiple images, arcs, and distortions. These effects preserve local light speed while dramatically altering global paths. Lensing measurements map mass distributions precisely because they depend directly on spacetime curvature rather than on assumptions about forces. Event horizons represent an extreme limit of this geometric influence. An event horizon forms when spacetime curvature becomes so strong that all future-directed null geodesics originating inside a certain region fail to reach distant observers. The horizon is not a material surface. It is a boundary in spacetime that separates events that can influence infinity from those that cannot. At an event horizon, light still moves locally at C. A freely falling observer crossing the horizon detects nothing special at that moment. Light rays emitted outward just inside the horizon remain trapped, not because they slow down, but because all future-directed paths lead deeper inward. The geometry tilts the light cones such that the outward direction lies within the cone pointing toward the interior. Escape becomes geometrically impossible. This one-way nature defines the horizon. Signals can cross inward, but no signal originating inside can propagate outward to distant regions. The causal structure enforces this asymmetry. The horizon thus represents a global feature of spacetime geometry rather than a local physical barrier. Time dilation near horizons accentuates the difference between local and distant descriptions. To a distant observer using coordinate time tied to faraway clocks, light emitted near the horizon appears increasingly delayed and redshifted. Emission events pile up closer and closer to a finite coordinate time. Locally, however, emission and propagation proceed normally. The discrepancy arises from how different observers slice space-time into space and time. The bending and trapping of light in gravity also influence causal structure more broadly. Light cones tilt and deform in curved space-time. The future and past regions of events change shape. In cosmology, this leads to particle horizons and event horizons that limit causal contact across the universe. In strong gravity, it leads to trapped surfaces and black holes. Despite these deformations, the fundamental causal role of C remains intact. At every point, light defines the boundary between time-like and space-like directions. Gravity alters the orientation and shape of that boundary across space-time, but it does not eliminate it or permit local violations. Causality remains encoded in geometry. General relativity therefore preserves the speed of light as a local invariant while embedding it into a dynamic space-time. Light does not slow under gravity. It follows curved paths because space-time itself is curved. Event horizons emerge when curvature reorganizes causal structure so completely that outward-directed null paths cease to exist. This geometric view unifies gravitational lensing, redshift, time delay, and horizon physics under a single principle. Light traces the structure of space-time. By observing how light bends, delays, and disappears beyond horizons, physics directly probes the curvature of the universe itself. The status of the speed of light as a fundamental constant rests on what is meant by fundamental in physical theory. The numerical value of c depends on the system of units chosen, yet its role in the structure of physical law does not. Distinguishing between numerical convention and structural necessity clarifies what c represents, why it links space and time, and what it would mean to consider theories in which it varies. In modern physics, c appears as a conversion factor between temporal and spatial measures. In relativistic spacetime, intervals combine time differences and spatial separations into a single invariant quantity. The constant c supplies the unit conversion that allows time to be expressed in units compatible with space. When spacetime intervals are written, temporal differences are multiplied by c to yield dimensions of length. This role does not depend on optics, it defines how spacetime itself is measured. The numerical value of c equals exactly 299,792,458 meters per second by definition in the International System of Units. This exactness reflects a choice rather than an experimental discovery. The meter is defined as the distance light travels in vacuum during a specified fraction of a second. By fixing c, metrology assigns uncertainty entirely to time measurement. Atomic clocks then determine spatial units indirectly. This convention highlights an important point. Changing unit systems changes the numerical value of c without altering physics. In natural unit systems commonly used in theoretical physics, c is set equal to 1. In such systems, distances and times share the same units. Velocities become dimensionless ratios. The equations simplify, revealing structure more clearly. Setting c to 1 does not remove the speed limit. It incorporates it into the geometry of space-time itself. The fact that c can be scaled away numerically sometimes leads to the claim that it is not truly fundamental. This interpretation confuses numerical representation with physical content. A constant is fundamental when it cannot be removed from the structure of the theory by redefinition without changing physical predictions. Although c's numerical value depends on units, its presence in transformation laws, causal structure, and dispersion relations cannot be eliminated. The deeper meaning of c lies in the way it links space and time. Before relativity, space and time possessed independent units and independent transformation rules. Velocities measured rates of change between them. Relativity unifies them into space-time, where transformations mix spatial and temporal coordinates. The constant c determines the slope of light cones and the relative scaling between spatial and temporal axes. It fixes the geometry. This geometric role explains why c governs more than light. It sets the maximum speed for all causal influences. Gravitational waves, massless quantum fields, and signal fronts all propagate at this speed in vacuum. The constant appears wherever causal structure matters, regardless of interaction type. Its universality signals a fundamental status. The link between space and time becomes explicit in Lorentz transformations. Relative motion mixes coordinates with coefficients involving velocity divided by c. Without c, no invariant distinction exists between time-like and space-like intervals. The constant determines which separations admit causal connection and which do not. It shapes the classification of events into past, future, and elsewhere. From this perspective, c resembles other constants that define space-time structure. Planck's constant sets the scale at which quantum effects become significant. Newton's gravitational constant sets the coupling strength of space-time curvature to energy and momentum. The speed of light sets the conversion between temporal and spatial dimensions. Each constant encodes a structural feature of the universe rather than a property of a particular phenomenon. The possibility of varying c theories arises when one asks whether this structural role could change. Could the conversion between space and time differ in different regions or epochs? Could the invariant speed itself vary? Addressing these questions requires careful separation of meaningful physical variation from artifacts of unit choice. Because c can be set to 1 by choosing units, only dimensionless quantities possess unambiguous physical meaning. A statement that c varies over time has no invariant content unless it refers to variation relative to other constants, forming dimensionless ratios. For example, one might consider whether the ratio of c to another characteristic speed or combination of constants changes. Many proposed varying c theories attempt to explain cosmological observations by modifying the early universe value of c. These models often aim to address horizon or flatness problems without invoking inflation. In such theories, c appears as a dynamical field or parameter that evolves. The challenge lies in defining what changes physically. If units are redefined at each moment, apparent variation may represent a choice of coordinates rather than a real effect. To make physical sense, a varying c theory must specify how observable dimensionless quantities change. It must alter ratios that cannot be absorbed by redefining units. This requirement severely constrains viable models. Moreover, altering c affects the entire causal structure of spacetime. Light cones would change shape. The distinction between time-like and space-like intervals would evolve. Consistency demands careful handling of causality, energy conservation, and covariance. Another difficulty arises from experimental constraints. Observations across cosmology, astrophysics, and laboratory physics show remarkable consistency in relativistic behavior. Atomic spectra from distant galaxies match local spectra after accounting for redshift. Particle interactions obey the same relativistic kinematics across energies and epochs accessible to observation. These facts constrain any variation in fundamental ratios to extremely small levels. Theoretical consistency also poses obstacles. Relativistic quantum field theory relies on Lorentz invariance to enforce causality and stability. Altering c typically breaks or modifies this symmetry. Preserving causality in such modified frameworks requires additional structure. Without careful design, superluminal modes or causal loops emerge. Some approaches reinterpret varying c ideas as effective descriptions rather than fundamental changes. In these views, the underlying invariant speed remains fixed, while effective propagation speeds in certain regimes differ due to background fields or emergent phenomena. Such interpretations align with known physics, where media alter effective light speeds without modifying spacetime structure. The distinction mirrors the difference between vacuum propagation and propagation in matter. In matter, effective speeds vary while c remains invariant. Extending this logic to cosmology suggests that many apparent variations could arise from evolving fields or backgrounds, rather than from changing spacetime geometry itself. From a more abstract standpoint, c appears as a parameter defining the symmetry group of spacetime. Special relativity replaces the Galilean group with the Lorentz group. The value of c sets the invariant speed associated with that group. Changing c alters the symmetry structure. In the limit where c approaches infinity, Lorentz symmetry reduces to Galilean symmetry. This limit corresponds to classical mechanics, where no finite speed limit exists. The success of relativistic physics indicates that the universe does not occupy this limit. Thus, c's fundamentality lies in the symmetry it defines. It separates relativistic from non-relativistic regimes. It determines how physical laws transform between observers. These roles remain regardless of numerical scaling. The historical evolution of units reinforces this view. Earlier measurements treated c as a quantity to be determined experimentally. Once its invariance became clear, metrology reversed the logic, defining length in terms of time and c. This reversal did not demote c. It acknowledged its centrality. The same reasoning applies to other constants. Planck's constant can also be set to 1 in suitable units, yet quantum effects remain real. The ability to absorb a constant into units does not diminish its physical significance. It reveals its role as a bridge between conceptual domains. In this light, the speed of light is fundamental because it expresses how space-time itself is stitched together. It links durations to distances. It defines causal order. It governs the transformation of energy and momentum. It appears wherever geometry constrains dynamics. Varying C theories challenge this structure and therefore face severe constraints. To succeed, they must reproduce known relativistic behavior while modifying deeper aspects in controlled ways. So far, no such theory has achieved widespread acceptance or experimental support. The question of fundamentality therefore resolves into structure rather than numerics. The speed of light matters not because of its measured value, but because it encodes the relationship between space, time, and causality. That relationship underlies all relativistic physics. Changing units changes numbers. Changing that relationship changes the universe. In this sense, C stands as a cornerstone. It does not merely describe how fast light travels. It defines what it means for anything to travel, to influence, and to persist through space-time at all. The speed of light functions as an organizing principle that shapes the architecture of physical reality at every scale. It determines how space-time is structured, how processes unfold, and how limits arise on what can be computed, observed, or influenced. Rather than acting as a contingent parameter tied to electromagnetic phenomena alone, C defines the geometric and causal framework within which all physical laws operate. Space-time acquires its structure through the existence of an invariant speed. In relativistic physics, spatial distances and temporal durations are not independent quantities. They form components of a unified space-time interval whose value remains invariant under changes of inertial reference frame. The constant CE provides the conversion between temporal and spatial components, fixing how they combine into a single geometric quantity. Without such a constant, space-time would not admit a stable classification of intervals into time-like, space-like, and null categories. This classification underpins causality. Events connected by time-like intervals can influence one another through massive objects or signals travelling below C. Events connected by null intervals connect through massless signals travelling at C. Events separated by space-like intervals remain causally disconnected. The invariant speed defines the boundary between these domains. Every observer, regardless of motion, agrees on which events lie inside or outside a given light cone. The geometry associated with this structure was clarified through the space-time formulation developed by Hermann Minkowski, where time and space appear as coordinates on equal footing, distinguished by the metric signature. In this formulation, C determines the slope of light cones and therefore the orientation of causal structure throughout spacetime. Physical laws respect this structure by remaining invariant under Lorentz transformations that preserve C. Once spacetime geometry incorporates an invariant speed, limits on interaction follow immediately. No physical influence propagates outside the light cone. Forces act locally and propagate through fields at finite speed. Changes in one region affect distant regions only after sufficient time has elapsed for signals to travel at or below C. This rule holds across classical fields, relativistic particles, and quantum interactions. Computation inherits these limits. Any physical computation requires the transfer and processing of information, implemented through physical systems obeying relativistic constraints. Signals connecting logic elements, memory units, or processors propagate at finite speed. As systems grow in spatial extent, communication delays become unavoidable. Parallelization encounters synchronization limits set by light travel time. No computation distributed across space completes faster than the causal connections allow. This limitation persists even in idealized models. Abstract computation models often ignore spatial separation, yet physical realizations cannot. The finite speed of information transfer enforces lower bounds on computation time for tasks requiring coordination across distance. These bounds scale with system size and C. In large-scale systems, latency becomes a dominant constraint. Observation obeys the same architecture. Observers receive information exclusively through signals propagating at finite speed. The past light cone of an observer defines the totality of accessible information at a given moment. Events outside this cone remain unobservable until causal signals arrive. This constraint structures astronomical observation, experimental measurement, and everyday perception alike. In cosmology, the speed of light defines horizons. Particle horizons limit how much of the universe has been causally connected since its beginning. Event horizons limit which future events can ever influence a given observer. These horizons arise not from material barriers, but from space-time geometry and finite signal speed. They partition the universe into regions of causal contact and isolation. The same principle governs extreme gravitational environments. Near black holes, space-time curvature tilts light cones inward. Event horizons form where all future-directed null paths lead inward. The speed of light remains locally invariant, yet global causal structure changes. The architecture of space-time enforces one-way boundaries that no signal crosses outward. The speed of light also constrains interaction rates. Forces mediated by fields propagate with finite delay. Electromagnetic, gravitational, and other relativistic interactions transmit changes through space-time rather than acting instantaneously. This delay stabilizes physical systems by preventing instantaneous global coupling. It ensures locality, allowing complex structures to exist without immediate collapse into global equilibrium. In quantum theory, C constrains the spread of correlations that can be used operationally. Entanglement produces correlations across space-like separations, yet no controllable signal propagates faster than light. Measurement outcomes remain locally random until classical communication, limited by C, allows comparison. This separation preserves consistency between quantum mechanics and relativistic causality. The invariant speed also limits how quickly physical systems can equilibrate. Thermalization, diffusion, and relaxation processes propagate disturbances through interactions constrained by C. Even in highly conductive or strongly interacting systems, equilibration fronts advance at finite speed. This behavior appears in condensed matter systems as Lieb-Robinson bounds, which set effective light cones for information propagation in non-relativistic quantum systems, reflecting deeper relativistic constraints. Energy transfer follows the same architecture. Energy moves through fields and particles at finite speed. Power transmission, radiation, and mechanical stress propagate causally. Shock waves, electromagnetic pulses, and gravitational waves all advance at speeds determined by local dynamics, bounded by C. The architecture prevents instantaneous redistribution of energy across space. The speed of light thus defines a universal tempo. It sets the maximum rate at which physical processes influence one another across distance. Time evolution unfolds within this constraint. Physical law becomes predictive because influences propagate with delay rather than instantaneously. The architecture extends to measurement itself. Clock synchronization relies on exchanging signals at speed c. Definitions of simultaneity depend on light propagation. Spatial coordinates derive from time measurements multiplied by c. Metrology embeds the invariant speed into the operational meaning of distance and duration. The same constant governs relativistic energy-momentum relations. Energy, momentum, and mass connect through c in a way that preserves conservation laws across frames. These relations prevent massive objects from reaching the null boundary. They maintain separation between matter and radiation in space-time geometry. The architectural role of C also shapes how theories unify. Electromagnetism, special relativity, general relativity, and quantum field theory all incorporate the same invariant speed. This consistency allows their domains to overlap without contradiction. Where theories extend or approximate one another, C remains fixed, anchoring transitions between regimes. The universality of this constant suggests that the universe does not merely obey a speed limit as an external rule. Instead, it organizes itself around that limit. Space-time geometry, causal order, interaction structure, and observational access all derive from it. The speed of light appears not as a parameter added to equations, but as a constraint that determines which equations are possible. This perspective aligns with the view articulated by Albert Einstein, who recognized that invariant signal speed reshapes kinematics rather than emerging from dynamics. Once accepted, the consequences unfold inevitably. Space and time deform to preserve C. Causality aligns with geometry. Physical law gains coherence. Within this architecture, limits acquire meaning. Some processes remain impossible, not because technology fails, but because space-time forbids them. Superluminal signaling, instantaneous computation, and global synchronization vanish from the set of physically realizable operations. These absences contribute as much to the structure of reality as the processes that occur. The speed of light thus functions as a rule the universe builds itself around. It defines how events connect, how systems evolve, and how knowledge accumulates. It shapes what can be known, how fast it can be known, and how influences spread. In doing so, it transforms a numerical constant into a foundational element of reality's architecture.